Hello everyone, my name is Ubaid Shah, and today we are going to discuss binary classification by using artificial neural network. Binary classification is most frequently and widely tackled problem in machine learning domain. To solve binary classification problem, we are having different machine learning algorithms such as logistic regression, decision trees, support vector machine classifier, random forest classifier, etc. But in this particular video, we are going to discuss binary classification by using artificial neural network. So very first of all, we need to understand what is binary classification. Suppose if we are having a data set where we are having features and labels, and these labels are of only two categories, such as 1 or 0, yes or no, male or female, approved or not approved. Okay, so this problem falls under binary classification. In this particular video, we are going to use artificial neural network in order to solve binary classification problem. Very first of all, we will first see theory behind artificial neural network. Then how can we use ANN for binary classification problem. Then we'll see some practical implementation by using ANN. Okay, so let's get started. Now suppose if we are having a data set like this, where we are having some features, okay, like x1, x2, x3, okay, and we are having one label y. Okay, so we know that whenever we are solving any machine learning algorithm, especially linear regression problem, that time we will be predicting the y hat value like this, right? Beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 and x3, right? And whenever we are considering some error, then we will be adding error term to it. Now, in order to solve any problem by using artificial neural network, very first of all, we need to form a neural network, right? So how can we form these neural network? Very first of all, this equation will be converted into a weighted form when we solving a neural network problem like this. Okay, so this is y hat is equal to w naught plus w1 x1 plus w2 x2 plus w3 and x3, and we are not considering this error term in this artificial neural network equation. Okay, now this w naught is nothing but the bias term. Okay, so we will be representing it by b0, and this w1, w2 and w3, these are the parameters, or you can say the weights. These are the weights. Okay, so this equation will be modified as y hat is equal to b naught plus w1 x1 plus w2 x2 plus w3 x3. Okay, so this is the normal regression equation, and this is the modified weighted form of that regression equation where we are not considering this error term. Okay, now in order to solve this by using artificial neural network, we are forming a network like this. This is the neuron number 1. we are going to form some neural network. Okay. So this is neuron number 1, 2, and 3. Okay. So these 3 neurons are present inside the input layer. Then we are having one more neuron. Okay. So this neuron will be inside the output layer. Right. And we are having one neuron over here. Okay. And that will be inside hidden layer. Now we will connect all these neurons like this. Right. Now, if we see that this one will be having the values like x1, x2, and x3. These are the input features, okay, inside this input layer. Now, this will be connected to this neuron, output neuron, okay. Now, at the output, we are having y hat, okay. Now, these lines will be assigned weights like this, W1, W2, and W3. Now, what happens over here? We are getting an equation, okay, which is similar to the y cap equation like this, okay. So when we multiply x1 with w1, we are getting w1 x1. Then we'll add the product of x2 and w2 like this, w2 x2. Then we'll add w3 x3, okay. Okay. Now, there is one more term called bias will be added to this one, okay, like this. So this will be the bias, okay. So that will be added over here, okay. Now, over here, if you see that we are having the summation of w and x like this, okay. So wi xi, where I varies from 1 to n, plus we are adding bias to it, okay. So this is equal to z. This is equal to z. So what happens over here in the hidden layer? We are taking the function of z, okay, and this function of z is known as activation. This function of z is known as activation, okay. Now, when this activation is triggered, that time all the information will be transferred towards the output layer, okay. So when we are connecting this hidden layer to the output layer, that time also we need to assign some weights over here. So suppose this is the weight of the hidden layer, okay. Now, this a term, which is calculated by this g of z, okay. So that will be multiplied like this, WHA, and here also we will be adding some bias term. Suppose this is the bias of the hidden, or you can say the bias of the output, okay. Now, this term is known as Z. You can say this is the Z output. And here also we will be taking the function of that Z output, okay. And this function of Z output will give us the value of Y hat. This will give us the value of Y hat. That is nothing but the prediction. Okay, now we are having some actual values of y, right? And when we take the difference between this y hat and y, so we will be getting some error. And in artificial neural network, that error is known as loss function. Okay, loss function. Now our aim is to minimize this loss function. Okay, after minimizing this loss function, we will be getting y hat closer to y. Okay, now how we can minimize this loss function? So there is an optimizer that is called gradient descent optimizer. Okay, gradient descent optimizer that is used to minimize this loss function. Okay, so there are so many optimizers present in artificial neural network, such as gradient descent, mini-batch gradient descent, stochastic gradient descent, okay, RMS prop, AdaGrad, AdaDelta. Then there is SGD with the momentum, and most widely used optimizer is Adam optimizer. Okay, now when these value of y are closer to this value, actual value of y. Okay, when this predicted value of y is closer to this actual value of y. Okay, so if you see over here that y is obtained by this z naught, right? And with z naught is obtained, or we can say it is dependent upon the weight and the bias, right? Here also, if you see over here that this z is dependent on the w and b, that is bias and the weights. Now if we modify all the values of weights and bias, then and then only we can achieve y hat or y predicted closer to the actual value of y. Okay, so how this will be achieved? This will be achieved by using the back propagation. So what happens in case of back propagation? Gradient descent algorithm is used. Okay, and this will modify the value of weights by using this formula. W new is equal to W old minus learning rate dl by dw old, that is nothing but the gradient. Okay, and eta is the learning rate. Similarly, this bias new will be obtained by this formula, bias old minus learning rate dl by db old. Okay, db old. So in this way, we can modify the values of weights and bias, and that will be fed into this neural network over here. Okay, after feeding all these values and modified, then again we will do some forward propagation. Okay, now in this forward propagation, again these equations will be formed and we will be getting y predicted. After that, again this process repeats. Okay, now over here, if you see, this process repeat again and again and again and again until we are getting a y predicted closer to the y actual value, right? This process is called training process. And during training process, we are modifying all the weight values multiple times. Okay, So if you see over here that we are having some trainable parameters over here. Okay, so let's see how many trainable parameters that are present. So again, if you see that this is the same architecture neural network. Okay, and all of them are connected. So suppose this is x1, x2, and x3 again, and here it is y hat. Again here w1, w2, w3, and then we are adding some bias to it. Again here we are having wh, and we are having bias of output. Okay, now here we are having activation function, right? Some activation value for this layer, and we are having again the activation value for the output layer, right? Output layer. Now if you see over here how many trainable parameters are present. So suppose if we are having this w1 over here, w2 over here, w3 over here. Okay, so 3 plus 1. So these are 3 plus 1, 4 parameters, like 3 weights plus 1 bias, right? So 3 plus 1 is equal to 4 trainable parameters present for the first hidden layer, right? In the second connection between hidden layer and the output layer, we are having 1 weight and 1 bias. Okay, so there are 2 trainable parameters. Okay, so there are total 4 plus 2 trainable parameters. That means 6 trainable parameters. Okay, now suppose if you are having a complex neural network. Okay, if you are having some complex neural network like this, suppose if you are having 1, 2, 3, and 4 neurons, and in the hidden layer, first hidden layer, we are having 3 neurons. Then in the second hidden layer, we are having 3 neurons. And in the output layer, if we are having 1 neuron, and when we connect all these neurons, okay, like this, and suppose if we connect all these neurons, okay, like this, we can change the color in order to understand completely. Let's suppose, right? And then we are having another neurons, right? So suppose if we are having, I will first connect all those things. Now suppose we are having weights in this input. This is W1, W2, W3, and W4. Then W5, W6, W7, W8, then W9, W10, W11, and W12. Okay. Now, as we all know that we can add the bias, right? So here the first hidden layer bias, this one is the first bias, then this one is the second bias, and this one is the third bias. Okay. Next, if we see this one is the first, you can say the WH1, WH2, WH3, right? And then this one will be the WH4, WH5, and WH6. Then last one is WH7, WH8, and WH9, right? Then again, if you see that we can add bias over here. So this is the bias of hidden, you can say, so hidden 1, 1, hidden 1, 2, and hidden 1, 3. We can give the name like this. So this is 2, 1, bias of hidden 2, 2, and bias for the hidden 3, 3, right? Then again, we are having some weights over here like WH, you can say the 2, 1, WH2, 2, and WH2, 3, right? Then again, we are going to add output bias. So this is the BO, right? Now, if we observe over here that there are total 12 weights that are present, okay, in this first layer. There are total 12 weights that are present over here. So how will we achieve these 12 weights? So if you see that this is the X1, this one is the X2, this one is the X3, and this one is the X4. And here we are having 1, 2, and 3. So when we multiply this 4 by 3, we will be getting 12, right? Now here, if you see that we are having total 9 weights. So how did we achieve? So there are total 3 neurons over here, and there are total 3 neurons over here. And when we multiply this 3 by 3, we are getting 9, right? Similarly, over here, we are having only 3 weights. Okay, so how did we get? So 3 multiplied by 1. Okay, so 3 multiplied by 1. So we are getting 3 weights, right? Similarly, here we are having 3 biases. So 1, 2, and 3. So we can having 3 biases. Okay. Again, here we are having 1, 2, and 3 biases. So we can having 3 biases over here, and we are having only 1 bias. So only 1 bias. So 12 plus 3, it is equal to 15. 9 plus 3 is equal to 12, and 3 plus 1 is equal to 4. Now, when we add all these values, so 15 plus 12 plus 4, so this is 15 plus 12, 27, 27 plus 4, 31. Okay, so 31 trainable parameters. Okay, so there are total 31 trainable parameters that are present over here. Okay, so the 15, 12, and 4. Now over here in this input layer, in between the input layer and the first hidden layer, we are having 15 trainable parameters. In the hidden layer 1 and hidden layer 2, we are having 12 trainable parameters, and in the hidden layer 2 and the output layer we are having 4 trainable parameters. So there are total 31 trainable parameters that are present. So in the back propagation we are modifying 31 parameters. Okay, now here if you see that we are having this activation, right? So activation function is used activation function is used to trigger the values, right? Very first of all we need to uh, understand what is the main aim of this activation function. So it is used to trigger the values, or you can say the in order to fire the neurons. Okay, so there are so many activation functions that are present. Okay, so there are like sigmoid activation function, then tanh activation function, then ReLU, then leaky ReLU. Okay, so these are most commonly used activation functions. Okay, so this sigmoid activation function we are using for the binary classification problem, and this sigmoid activation function always used in the output layer. Okay, so this G is nothing but the sigmoid activation function, so this is represented by sigma. Okay, now in between in the hidden layers, ReLU activation function is most commonly used activation in the hidden layers. Okay, but whenever we are solving binary classification problem, we will always use sigmoid activation function at the output. The output of the sigmoid activation function is always in between 0 to 1. So this will be acting as the probability. Okay, and as we all know that we will be just having two values in the output, therefore we will be preferring, or we always use sigmoid activation function. So sigmoid activation function is very similar to the logistic regression problem, or you can say the logistic regression function. Okay, so there we will be having only like this one. Okay, the shape of that activation function, the shape of the activation function will be like this. If we are having 0 value over here and the 1 value over here, then we can consider that this one is the 0.5 value, like this. Okay, so if we consider that this is A and this one is Z, okay, so the value of this activation function, that is G of Z, that is nothing but A, will be 1 divided by 1 plus e to the power minus Z. Okay, 1 plus e to the power minus Z. So this is the function of the activation function. So if you take the derivative of that activation function, so it will always vary between 0 to 0.25. Okay, so this activation function always varies between 0 to 1. Okay, 0 to 1. So this is like this line. Sorry. Okay. So it will always vary from 0 to 1. Now, if we see over here that at the highest or maximum values or minimum values of the Z, this will not change. Okay, this will not change. Now, this is about the activation function that is used in the binary classification problem. Now, there is a loss function. Okay, so if you see over here, so there is a loss function called binary cross entropy. Binary cross entropy. This binary cross entropy loss function is used in case of binary classification problem. Okay, this is the equation for the binary cross entropy. Okay, so this is the loss function formula. So where you see 1 by n minus 1 by n, actual value of y multiplied by log of predicted value of y plus 1 minus actual value of y multiplied by log of 1 minus predicted value of y. Okay, and where I varies from 1 to n, where n is entries that are present. So this is the loss function that we are going to use in case of binary class classification problem. Okay, I hope you have understood all these things. So let's see the practical implementation of the binary class classification problem by using the artificial neural network. Here is a loan prediction problem that we are going to solve by using ANN. Okay, now I have created one notebook and the code is already written over here. So I'll just explain all the things to you. Okay. Before proceeding ahead, we need to understand how we are going to approach the problems. Okay. So very first of all, we will pre-process the data. We'll find some missing values in our data and we'll impute all these missing values. Then we will normalize all the values. We will convert everything into numerical values. In our label column, we are having yes or no type or male or female type classes. Then we will convert that into 1 or 0. Okay, and 1 and 0 always be present in integer format. Okay, we cannot use that in the float format. Then second step will be we define the architecture of the model. Okay, so how the input layer and output layer will be there, how many neurons in the input layer, how many neurons in the hidden layer, and how many neurons in the output layer. Then since this is a classification problem, we will be using sigmoid activation function as we have discussed earlier, okay, in the output layer. Then after that, we will train the model, okay. Then we are going to perform some, you can say, the pre-processing on the test set as well. We will generate the predictions for the test set, okay. And after that, we will be saving all the information in the CSV file, okay. Now, the first step is to import library like NumPy and Pandas in order to read the data set. So we are having total 2 data sets, train data set and the test data set. Okay. So for that, we are creating data frames like train df and the test df by using pd.read_csv. Okay. So in the train df, we are using train CSV file, and in the test df, we are using test CSV file. Okay. So when we explore our data in the train df, we are having these columns, okay, loan ID, gender, married, dependents, education, self-employed, then applicant income, co-applicant income, loan amount term, credit history, property area, and the loan status. Okay, so loan status is our label column where we are having yes, no values. Okay, so we will first find out, is there any missing values present in our data? Okay, so train df.isNull.sum, it will give us the total count of the missing values. Okay, so here if you see in the gender, we are having 13 missing values, married 3, dependents 15, okay, self-employed 32, loan amount 22, loan amount term 14, and the credit history 50. Okay, now we'll see what are the data types of that particular columns. Okay, so in order to know the data types, we are using train df.info. Okay, so the .info method is used to see the data types and the complete information about the total number of entries that are present in our data set. Okay, so gender is object, right? Married is object, dependents object, object. Okay, and then integer, then float, and then object. Now, as this is the neural network problem, so we need to convert everything into numerical values. Okay, in the pre-processing step, what we do, we will do some missing value treatment. So if we are having categorical variables, then we will be filling it by the mode value. Okay, and if it is a numerical variable, then we will be filling it by the mean or median value. Then we will convert categories into numbers by using one hot encoding or label encoding. So there are three to four methods that are used to convert categories into the numbers, right? One hot encoding, label encoding, or the mapping method. So we will be using one of those. Then we will be scaling down, you can say, the values, and scale everything into in between 0 to 1. Okay, so for that purpose, we are using a normalization method. Okay, so this normalization will helps in reducing the time complexity, and the and our neural network will converge very fast. Okay, so let's see. This is the gender, and when we apply so gender column over here is a categorical column, and when we apply mode, so it will give us a result like this. Okay, 0 or male. Now when we use a square bracket 0, then it will give us the value male. Okay, so this is the mode value in the gender column that is representing that there are more males present in the gender column. Okay, so what we do, for all categorical data, we will be filling NA values like this one. Okay, mode and then square bracket 0. Okay, so in gender column, fill NA train DF gender dot mode 0 in place equal to true. So it will replace all the null values with the mode values of that particular column. Similarly, for the married column, dependents column, self-employed, loan amount term, and credit history, we'll be replacing all the null values with the mode values. Okay, after that, for the test data, we are doing the same thing. Okay, so for all categorical values, we are replacing all the null values with the mode values. Okay, then there is loan column, and loan column is the numerical column. So we will be filling all the null values with the mean data. Okay, so we will be filling that with the mean data. Similarly, we will be doing fill NA, or you can say the missing value imputation in case of the test data. Okay, now after doing that, we will check, is there any null value present? So here, if you see, there is no null value present. Okay, now we will be converting all the categorical column into numbers. Okay, so we will be using the map function. So in the map, so for the gender column, we'll map male with 0 and female with 1. In the married, no with 0 and yes with 1. In the dependents, 0 with 0, 1 with 1, 2 with 2, and 3 plus with 3. Okay, for the education, we will map graduate with 1, not graduate with 0. Self-employed with in the self-employed column, no with 0, yes with 1. Then in the property area, for the rural, 0, semi-urban 1, and urban 2. Then for the loan status, N, if it is N, then 0. Then if it is Y, then 1. Okay, so same in case of the test data. After doing this, what we do, we will be scaling down our data. We will be normalizing our data by using this normalization equation, that is x minus x min divided by x max minus x min. Okay, so this will convert everything in between 0 to 1 values. Now here, if you see that in the dependents column, we are having values like this, 0, 1, 0, 1, 1, right? If you see the data trained here, so in the loan ID, we are having these values. In the gender, married, and dependents, education. So all the values are like this. Okay, so this is, you can see In the applicant income, we are having values in the thousands. Loan amount, we are having values in the hundreds, right? Loan term, we are having values in hundreds, right? Here we are having in some digits, and so on and so forth. Okay, so what we do, we will be normalizing everything in between 0 to 1. So we will not consider this first column, loan ID. After that, we will be considering all the columns. Okay, so we are using this for loop for I in train DF from column 1 onwards. Train DF I is equal to train DF I minus train DF I dot min divided by train DF I dot max minus train DF I dot min. So what it will do, it will first go to this gender column. In that gender column, it will be considering this first entry, that is 0. Then it will then the minimum value of this gender column will be subtracted from this first value, then divided by the maximum value of this gender column minus minimum values of this gender column. Okay, so what it will do, it will calculate the values in between 0 to 1 only. Okay, now if you see over here that in the dependents, we are having values like 0, 0 0.3 and all these things. Okay, so it will be converting all the values in between 0 to 1 only. Okay, now when we check the data types of our data set, so we observe that everything is converted into float apart from this first column, because we haven't done anything on that. Now this column is not required for our analysis, therefore we will be dropping this column. Okay, so train df dot drop loan id access equal to 1. We are going to drop that one. Now we will be forming a neural network. Okay, so we will be defining how many input neurons that are present in the input layer. Then in the hidden layer, we will be having two, you can say, hidden layers. Okay, because we are forming a deep neural network. Okay, and in the output layer, we are having only one neuron, because this is a binary classification problem. Okay, now for the loss functions, we will be having binary cross entropy. Okay, and for the optimizers, we will be using Adam optimizer. Okay. Then for the training purpose, we will be defining the number of epochs, that is a 50 number of epochs. Okay, so and after that we will be evaluating our performance. Okay, so very first of all, we will import some libraries like import matplotlib.pyplot as plt, import cborn as sns, import sklearn. Okay, import sklearn.model selection, import train test split, then from import matplotlib.pyplot as plt for graphical representation. Then cborn is also for the visualization, sklearn library. Then from sklearn.model selection, train test split, and for the accuracy score, from sklearn.metrics, import accuracy score. Okay, then we will form x and y. Okay, so x are the features and y is the label. So in the x, we will drop loan status since it is a label, and in the y, we will be storing loan status. Okay, when we check the shape of our data set, so there are total 614 rows and 11 columns, and in our y, that is for the label data set, we are having 614 values. Okay, now we will do some train test split. So before that, we'll see how the values are distributed inside the label column. Okay, so for that, I am using y dot value counts normalize equal to true. So if you see over here, For yes, we are having 68% of data. And for no, we are having 31%. So you can see that the data is not normally distributed. Okay. So maximum values, or you can say this one is the skewed data. So in this case, when we are not having normally distributed data, we are using stratify method for our sampling. Okay. So for X train, X test, Y train and Y test, we are using train test split. In that we are having X and Y, stratify Y. So we are applying stratify method on Y. So what it will do, it will split our data set in such a way that in the Y train and the Y test, we are having same proportion of 1 and 0 values similar to the actual values. Okay, like here, if you see that 1 is present 68% and 0 present 31%. After doing stratify, so in the Y train, when we see the value counts, so 1 present 68% and 0 present by 31% proportion, right? Similarly, in case of Y test, we are having around 69%, okay, which is very similar to the 68%. And here, this one is the 30%, okay, which is very similar to the 31%. So whenever we are using stratify method, so it will be splitting our data set in such a way that in Y train and Y test, we are having same proportional data similar to the original data. Okay. Then our test size will be the 20%, and we are using random state equal to 1. Okay. So we have just train test and split our data set. Okay. Next. Now, this is the deep learning problem. So for that purpose, we are using TensorFlow library. So import TensorFlow SDF, and as we can see for this, you can say tutorial purpose, I have used a 2.10 version of the TensorFlow. Currently, the latest version of the TensorFlow is 2.13, but as I am running it in my local machine, therefore I am using 2.10 version. Okay. Now we will be creating a model. Okay, so we are having some input layer. Then after that, we are having hidden layer, and then we are having output layers. Okay, so how this will be created? So in order to create that kind of neural network, we are using sequential model. Okay, so in order to use that sequential model, we are using from tensorflow.keras.models import sequential. This will create a sequential architecture of our neural network. Okay. So in order to form the layers, we are using from tensorflow.keras.layers import input layer and the tens layer. So input layer is for the input layer and tens is for the hidden layers. Okay. Hidden layers and everything. Now, very first of all, we will check what is the shape of our X10 data set. So that is 49,491 by 11. Okay, so this is our training data set shape. Next, our the value that is present over here is 11. Okay, so that will be displayed over here only. Okay, so there are total 11 columns that are present. Now these 11 columns, or you can say the number of features that are present, that will be used as number of neurons in the input layer. Okay, so what we do, we will be using this input neurons is equal to X train shape 1. Okay, and what is the value of this shape 1? That is the number of columns that are present in our data set. Okay, now we are having two hidden layers. So number of neurons that are present in, or you can say we are defining for the first hidden layer 10 neurons and the second hidden layer 5 neurons. Okay. Then for the output layer, we are having only one neurons, since this one is the binary classification problem. So we can only use one neuron. Okay. After that, we will be forming the architecture. Okay. So model is equal to sequential. Model dot add first input layer. And what is the shape of the input layer? So input shape is equal to input neurons, that is 11. And we are giving the name to that input layer as input layer. Okay. Then we are adding two hidden layers. For that, we are having neurons is equal to neuron hidden layer 1, that is 10 neurons. And we are using activation function as ReLU. Then we are giving the name to that particular hidden layer as hidden layer 1. Then I will add second hidden layer. In that, we are having neuron hidden layer 2, that are 5. Activation function is ReLU and hidden layer is 2. Then we are adding third hidden layer, or you can say third dense layer, and this dense layer is nothing but the output layer. Now, number of neurons that are present in the output layer is 1, and we are using sigmoid activation function, and we have given output layer as a name to that dense layer. Okay. After that, we'll check the summary of our model. So here, if you see that in the hidden layer, yes, hidden layer 1, we are having 10 neurons. In the hidden layer 2, we are having 5 neurons. And in the hidden layer 1, we are having 1 neuron. So if you see that there are total 120 parameters for the hidden layer 1. Then for the hidden layer 2, we are having 55 parameters. And for the hidden layer 3, we are having 6 parameters. So how did we achieve this? Okay, so if you see that in the input, we are having 11 neurons, right? Then in the neuron present in the first hidden layer are 10. And the biases that we are going to add are 10. Okay, so 11 multiplied by 10 plus 10, it will give us 120 value, right? Similarly, for the second hidden layer, we are having 5 neurons over here and the 10 neurons over here. So 5 multiplied by 10, 50. And there are total 5 biases are present. So it will give us the value 55. Okay. Similarly, for the output layer, total 5 neurons are present in the hidden layer. 1 neuron is present in the output layer and 1 bias is added. So total give us 6. Okay. So in this way, we are having total 120 plus 55 plus 6, 181 trainable parameters. Okay. So the weights and biases are 181 in our case. Okay. Next one is we will compile our model. Okay. And during compilation, we are defining the loss function and the optimizer. Okay. So loss function is binary cross entropy and the optimizer is Adam optimizer. So optimizer is used to modify or redefine the weights based upon the binary cross entropy. Okay. And we will be checking the accuracy of the model based upon the accuracy. Okay. Then before training, we'll see what is the data type of white test. So white test is having a float data type. So we will be converting that into integer like this. Okay. So white test dot as type int 32. When we check it, it is 0, 1. So that is integer data type. Similarly for white red, we will be converting our values into the integer. Okay. After that, if we see the X test, okay, so this is the X test. Now we will fit our model. Okay, so this is the training step. So what we do, we will fit our model X train, Y train. We are validating our model, okay, based upon the X test and the Y test, and we are running 50 epochs in order to train our data set. After running these 50 epochs, so it will give us the accuracy. In the accuracy is 0.829 for the validation, and for the model accuracy it is, or you can say that for the training accuracy it is 0.80. so if you see that this accuracy is quite you can say the close, okay, so we cannot say that this is the overfitted model or underfitted model. This is the best fitted model because validation accuracy and the test training accuracy both are similar. Therefore, we can say that our model is best fitted. Okay. Now, in order to you can say define the threshold value. Okay, so because this one is the classification problem, binary classification problem, and we need to very first of all find out the threshold value. Okay. And we know that we are using ROC AOC curve in order to find out the threshold value. So in artificial neural network, so this is the way to find out the threshold value. Okay. So as we know that for the sigmoid activation function or the probability, when we are having the threshold value 0.5, if the value predicted value, if the prediction is more than 0.5, then we consider this as 1. And when value prediction is below 0.5, then we consider this as 0. Okay. So always we are having two values, 0 and 1. But this is not always true because for different data sets, we are having different threshold values. So in order to find out these threshold values in our data set, we are using this method. Very first of all, we will predict the values for the X test. Then in the Y hat, we are finding the maximum values of the, you can say, prediction. Okay. So it will give us values like this. Okay. So these are the probability values, or you can say the maximum values for each record. Okay. For each record, these are the values. Okay. So these are the probability values that are present. Now, if we check the Y hat, so these are the Y hat values. Okay. Now we will plot ROC AOC curve by using this method. Okay. After plotting this, we can see that our 50% line and the logistic regression, or you can say the binary classification line for is merged or overlap on each other. So we will be considering 50% as our threshold only. Okay. So therefore, we will be predicting our model by using this threshold. So model.predict X test. If the value is greater than 0.5, then we will be converting that into 1. Otherwise, that will be converting into 0. Okay, so as type int will convert everything into an integer. If these values falls in the upper half, that is, if it is greater than 0.5, then we will be considering that as 1. Okay, because this will give us value in terms of, you can say the true or false. Okay, right? So if this is true, then that will be converted into 1. If this is false, then that will be converted into 0. Okay. Now after that, we will be checking the accuracy. So our model is 82% accurate. Okay. Then we'll be using precision recall F1 score, since this is the classification problem. So in order to validate, or you can say evaluate, in order to evaluate our model, we are using these accuracy scores. So here our value of precision is 0.8, recall is 1, and F1 score is 89. Okay. After that, we will be using this confusion matrix. Okay, so in this confusion matrix, if you see over here, so the false values are 17s and the true values are 85s. Then these false values, true predicted values are 85, and the false predicted values, actual false predicted values are 17. Okay, and the values which are, you can say, false but predicted as true are 21. Okay, now we can use this classification report where we are having for the 0 and 1 precision, recall, F1 and support values. So there you can see we are having the accuracy of 83%. Okay, now if we visualize our performance of the model based upon our history of the model, so this you can see this is the training and this is the validation. So these are like close to each other. So there is if you see the accuracy curve over here, so this accuracy is also very close to each other. Okay, so as we started our number of epochs, so as it goes, okay, towards the higher number of epochs, the accuracy increases. Okay, and it becomes stable after some 40 epochs, right? After 40 epochs, validation accuracy becomes stable. Now we need to predict the values and attach it to our test DF. So as we see over here that our test DF is having columns where loan status is not present. Okay, so this is our test data set. So all the values that are present over here are thousands and hundreds and hundreds. So we will first convert that into the normalized form. So we will do same, we will apply same equation, okay, to this test DF. Then we will predict the values for that test DF. Okay, then after prediction, we will be getting values like this one. Okay, between 1 and 0. Then what we do, we will add one more column, that is loan status, to the test DF, and we will be you can say adding that predicted values and map y to 1 and n to 0. Okay, and when we check the test DF now, so there we can see we are having loan status added over here. Okay, so for each entry we will be having some loan status, right? Now if you see in our test DF the status of the loan, so y present 84% and the no present 15%. So we can see that loan status is not approved for the 15% of the people. Okay, so in this way we have used or implemented our binary classification model to artificial neural network. Okay, so I hope you have understood each and everything. If you like it, so please subscribe to my YouTube channel. Okay, and please comment if you are having any query, and if you are having any suggestion, then please comment in the comment box. Okay, so thank you very much for watching this video. I hope you enjoyed a lot and you understood lots of the things regarding this binary classification. Thank you very much.